Hey guys, welcome to chapter 10, the last chapter in this semester of chemistry. So, for chapter 10, we're going to talk about gases. So, when you think about gases, the first thing that probably comes to mind is pressure. So, pressure is certainly one of the properties that we're going to use to discuss gases. So, what is pressure? So pressure for us as chemists is going to be the result of collisions between gas molecules or gas atoms and the surfaces around them. So if you think about tire pressure, for example, for us as chemists, tire pressure is going to be all of the molecules inside of that tire bouncing against the rubber inside that tire. And as those gas molecules bounce against the rubber, it creates a pressure. So that's how we're going to study pressure for chemistry. There is a formula for pressure. We're not actually going to use this formula to calculate pressure. But for those of you that are mathematically oriented, this might be a good picture for you to be able to understand what pressure is. So pressure is defined as the force exerted per unit of area by gas molecules as they bounce against the surfaces. So let me give a pointer here. So pressure is going to be the amount of force, the number of collisions for a given area. So here we see two containers. Let's assume that both of these containers are the same size. So that means the area would be the same. So this bottom variable is going to be the same. This guy over here on the left is going to have a lower pressure. Why does it have a lower pressure? Well, less particles inside that container means there's going to be less collisions with the side of that container, so it's going to register a smaller force. So that's why this one would be a lower pressure. Again, same size area. We've got more particles inside of this container. So more particles means more collisions with the size of that container. It's going to register a greater force. So it'd be a higher pressure because this number on top would be a little bit bigger. Okay, so just a closer look at how we study pressure. Units for pressure. So the unit that we're going to use the most is going to be ATM or atmosphere. So this is defined as the average pressure at sea level. So us here in Wilmington, we basically live at sea level. So the ATM around us is going to be around 1 ATM. The SI unit is technically a Pascal. So if you were to take some sort of physical science class or a physics class, you'd be dealing with Pascals. I'm excited that we use ATMs just for this reason right here. 1 ATM is a lot easier to deal with than a ridiculously large number of Pascals. But there's a conversion should you need it. And then another pressure unit you'll see is something called millimeters of mercury. So how in the world do we use a length measurement, millimeters, to measure pressure, right? So this is how barometric pressure is often given. Gracious. This is how barometric pressure is often given, often measured, as in millimeters of mercury. So let's look at a very simplistic barometer, and we'll get to know this idea of millimeters, a length measurement to measure pressure. So here's our barometer. What we've got here is kind of a reservoir at the bottom, and then this is an evacuated glass tube. So there's a vacuum inside of this glass tube. Inside of our reservoir is mercury. So that's how we get millimeters of mercury. So we're dealing with mercury inside of this reservoir. So mercury is in here. So as atmospheric pressure rises, it's going to push down. It's going to push down on this reservoir here. And as it pushes down on this reservoir, because it feels that pressure, the mercury is going to travel from the reservoir into this evacuated tube or this vacuum here. So at sea level, atmospheric pressure pushes down on the reservoir, mercury rises, and from the bottom of this tube to the top would be roughly 760 millimeters in length. So that's where our length measurement comes from. If atmospheric pressure drops, so this reservoir would not feel as much weight pushing down on it. So if atmospheric pressure drops, this reservoir would fill up a little bit, which means the mercury would come down out of the glass tube into the reservoir. So as atmospheric pressure drops, we might register a 745 millimeters. So that would be the length inside of there. So that's how we get a length measurement to measure pressure. So the last thing we're going to talk about in this first video is the kinetic molecular theory. So the kinetic molecular theory is the simplest model for studying the behavior of gases. So in this model, we are going to make some assumptions, and we'll talk about those as they come. But these assumptions are going to make our lives a little bit easier. So by understanding these assumptions, we're going to deal with algebra in this chapter rather than calculus. So just some assumptions to make the math a little bit easier and some of the concepts a little bit easier to understand. So in this theory, gas is going to be a collection of particles that are in constant motion. So when we've got a container full of gas, those particles are going to constantly be moving and bouncing all over the container. So particles of a gas are constantly moving. We're going to say that the attraction or repulsion between the particles is negligible. So are the particles going to be attracted to each other once in a while? Technically, yes, they are. But that attraction is so fleeting and so small that we're just going to ignore it for this chapter. And this is one of the major assumptions that gives us algebra instead of physics or instead of calculus. If you've ever taken a physical science course or a physics course before, you've heard things like ignore friction. Well, friction exists, right? But you ignore it to make the problem a little bit simpler. Same thing is going on here. Ignore the interaction between those particles. So there's a lot of empty space between gas particles compared to the size. So if I were to draw a little dot on this computer screen right here, that dot would represent one gas particle, and you may not see another gas particle until you get into the bathroom in your house or your apartment. So that's how far apart these particles are going to be. So lots and lots of empty space between the particles. So the average kinetic energy of a gas particle is directly proportional to the temperature in Kelvin. So lots going on in this statement. First thing, we're going to talk a lot about proportionalities in this chapter. But first statement here says kinetic energy is directly proportional to temperature. What that directly proportional means is that when one goes up, the other goes up. And when one goes down, the other goes down. So as kinetic energy goes up, that means those particles are moving faster. What's also going to go up with it? The temperature. And then vice versa, as kinetic energy decreases, so those particles slow down, the temperature of those particles is also going to go down. So there's a direct relationship between kinetic energy and temperature. And we studied this in chapter 9, actually. We saw that the type or the form of kinetic energy that we study is very much related to temperature. And then the collisions of one particle with another or the walls of the container is completely elastic. So what that means is that when two particles come into contact with one another, we're going to assume that no energy is exchanged between that collision, that they're simply going to bump into each other and leave in a different direction with the exact same amount of energy. That is not how things happen in real life. There is an exchange of energy when that happens, but we're going to ignore that exchange, again, just to make life a little bit simpler. This would be an example of an inelastic, so the opposite. So when two particles come together, there's certainly going to be some sort of stickiness going on or repulsion. They're certainly going to exchange some heat or exchange some energy. So this is reality, but we're going to live right here to make life a little bit easier in this chapter. That's it for this first video. That's just kind of an introduction to this gas chapter, to pressure, and then the position we're going to take as we go through this chapter. I hope you guys found that helpful.